actually great contributors. Okay, they're actually contributors to the ROS2 navigation project. Maybe you might have heard of NAV2 before. This two of them are actually great contributors to the project, and it's really a privilege and an honor to have them in our midst to share some things with us I think will benefit the community at large. And I know that what we should just get the best. And as you listen, prepare your questions and answer. There'll be time for question and answer. And so because of time, not to waste much of our time, I'll be introducing the first speaker. Then after the first session, Mr. Sikiru Salau, who is also the ROS community coordinator here in Nigeria, will be introducing the next speaker, and that's how we're going to go about this meetup. And I hope you get the best from this meetup. So now to the first part of this meetup. I'll be introducing our first speaker. But before I introduce the first speaker, I wanted to mention something which is very important. Hello? Like someone's mic is on. Hello, there's someone's mic is on. Okay, thank you. Yeah, I said before I introduce the first speaker, while going through the registration link, I noticed that one of the things there are a few things I noticed that there are a lot of, should I say, beginners or people that have not even, yes, they have 0 to 1 year experience in ROS. Beginner, that is, some are finding, most likely, I believe some are finding how to get started with ROS. I also saw some of the comments and the suggestion of some of the people. And one of the things I noticed generally is that there's a lot of people that have not started ROS, and most likely there are also other people that are finding it hard to get started with ROS. And I think one of the big problems is most likely the issue with a lot of us are using Windows, some of us are on Mac, to start changing, doing dual boots, and all these other different things, can really put a lot of people off, from getting started with ROS. And that's why this particular session is actually very, very important for you guys. I'll be introducing our first speaker. His name is Sakshay Mana. I hope I pronounced it well. Sakshay Mana is the senior associate and a software engineer at MathWorks, for those of you that know about MathLab. So he's one of the senior engineers there. And like I said earlier, he's also one of the contributors to the NAV2 project. That is the navigation 2 project that we all know about. And he actually worked on an interesting and useful project that will help ROS2 developers to get started. I believe it will help you to get started with ROS2. All these problems that, hindering people from getting started with ROS2. I believe his work will actually help you get started with it. And that is exactly what he will be presenting and be informing us about. So I want you to stay put, listen, and prepare your questions and answer at the end of the section. And I believe to be a very, very insightful one. So thank you very much as I introduce Sakshay Mana to give his presentation. Thank you.
Yeah, thank you. Thank you for the introduction. And thank you for inviting me. I'll just share my screen. Can you see my screen?
On my end here, not yet. I've not seen screen. Please, if you can't. Okay, I can see it. I can see on my end here. So as many that can see the screen, also give a thumbs up. That'll be well appreciated. Yeah.
Okay. Okay, so I'll be going into presenter mode now. I'm not able to see Teams, so if you have any doubts, just feel free to just let me know, stop in the middle or fine. Okay, let's start. So I'll be talking about ros2env. This is just like Samuel introduced. This is a software that I developed for simplifying development environments for ROS2. Now, just a brief or side note, although I work at MathWorks, this is not related to MathWorks, and this is just an open source contribution for the people and a problem that I faced, a solution to that. So let's start with this question, how to get started with ROS. So just like Samuel said, that most of the people that were joining are mostly beginners, and I would expect some people are doing ROS as well. So there's a mix I would expect. So let's say you are a junior, you are just starting out with ROS, and you just talk with someone who is already working on ROS, and you ask them this question: how to get started with ROS? Or let's say if you are an engineer working with ROS or on ROS, and someone asks you how to get started with ROS, the answers would include go through the tutorials, go through this YouTube video, go through this documentation and everything. But there is one common point among all the answers, which is install ROS and start building projects. So I guess we all being engineers, the basic thing or basic instinct to learn anything is just to install that software and start building projects on top of it. That's the best advice or best way we get started with anything. So now this gets us to the question for installing ROS. Now, how do we install ROS? Let's say you are a, or let's say at least I was when I started learning ROS, a regular Windows person. You have a Windows computer, and how do you install ROS or how do you get started with ROS? Now, there are various different ways we can start learning it. One is a direct Windows installation method. You directly install on Windows. Uh, a second way would be that you install WSL, which is Windows Subsystem for Linux. So WSL is basically a software that Microsoft ships in order to run Linux software on a Windows system. It's, you can call in very simple words, it's a virtual machine, but still not a virtual machine. So yeah. Next way would be dual booting a Linux system and then install ROS on it. That's one way you can do it. Another way would be you install a virtual machine software. Like over here, I have Oracle VirtualBox, but there are other VMware and other virtual machine software that you can install and then install the Ubuntu operating system on it and then install ROS2 and start with your projects. And one final way would be installation on Docker. You can install do Docker desktop on, or simply you can install Docker on your current Windows system. And then you can create certain images which are relevant to your project and get started with it. So these are some of the ways which I have found people use, and I have personally also tried all these things, how to install ROS and work with it. This is just to note, not an exhaustive list. There may be other methods also which people use and certainly can use to install ROS, but this is the most common ones which I have seen throughout my journey of learning ROS. So let's start with the direct Windows installation. Now, this would be, I would consider, or anyone would consider, an ideal development environment. It's something like you install Python on your Windows machine, you start making Python projects. It's as simple as that. This ideally should be as simple as that. But the problem with Windows is when you install ROS2 on your Windows system, you have to install multiple dependencies. You have to build libraries from source like Gazebo, Arvis, and you have to spend time debugging and fixing the issues. Now, although it is not impossible to install ROS on a Windows system, but if you go through this journey, It's a very long one, and you just stop. And you will become an expert in installing ROS on Windows rather than an expert on working on ROS. So although I have seen people doing it, but it's still a very complicated thing to do. So this is all for the Windows installation system. Then going on to installation on WSL, like I said, WSL is Windows Subsystem for Linux. It's a piece of software that you can install on your Windows machine, and you can run Linux based commands, Linux based software on your Windows machine itself. Very similar to virtual machine, but little different. This is again the most near perfect and almost straightforward solution, as you get an Linux environment on your Windows system, and you can then install ROS, which, yeah, you can follow the instructions and install ROS2, which is again not that difficult if you have a Linux system. But the problem with this one is that there is a chance of system pollution. Now you have a single system in which you will have all your ROS2 projects. Let's say you started working on a mobile robot. So you will have all the dependencies for that. And let's say you start working on a robot arm project, and then you'll have all your dependencies in that same system. Now, this kind of thing causes some system pollution, and there may be some library mismatches, and it creates a complete mess kind of situation. So that is one problem when you install it on when you install ROS2 on WSL. The next method is dual booting a Linux system. This is the expected path to follow. You should have a Linux machine if you are like a very professional person working with real robots and everything. You're expected to have a Linux system so that you can have all the drivers, you can install all the drivers easily. ROS2 also works almost the best on an Ubuntu machine. But the problem with this is, if again we are assuming we are a Windows machine user, this kind of thing is very difficult to do and quite risky to do as well. You may end up corrupting your complete system. Well, it happened to some of my colleagues or friends earlier when they tried to install a Linux system. And even I think my laptop also got a bit damaged while doing this. So this is quite a risky play if you want to do. Getting on the next one, installation on a virtual machine. This is once again a straightforward solution. So this is very ideal and very good solution if you want to go with this one. You install a virtual machine software on your system and then install a Linux operating system on that virtual machine and install ROS2 and get started. But the thing with this one is it requires setting up virtual machine. So how a virtual machine software works is it will directly emulate a desktop system on your Windows machine. It will simulate or emulate all the different ports, network adapters, Wi-Fi adapters, and everything. It's like you are running a computer system on top of a computer system. This makes the complete setup quite heavy, but you can still get your work done with this. Then going on to the last one, which is installation on Docker. Now, the Docker solution is quite straightforward and flexible. It's again, if you were to consider VM versus a Docker would be much better compared to a VM. Now, what Docker does, it doesn't directly emulate everything, only certain parts which are required to run the system. So those who, let's say, new to the Docker system, I will just briefly explain the concept for Docker. Now, developers or software engineers, we usually face this problem. So let's say I am a developer and I develop some piece of software that is working on my system. Now, for the other people to use it, I will send that complete software or package that and send it to the other person. Now, the problem is that there is an issue of it works on my system. So someone else will install that install that software on their system, and there is a high chance it will not work because they may have missed certain dependencies. Docker solves this issue using containers. Now, containers are created using images. Images is like a blueprint for creating software. They will write out, the images will write out the instructions for how to install a certain software, and container will follow those instructions and create an object out of it. Now, a developer like me, I will share that container with some other person and they can run that container. It will directly simulate the exact same settings which I had on my system on their system. So that's the concept of Docker. And that's why I think you can see why how it will work for ROS2 as well. I will just install ROS2 on a container and directly send it to the other person. They would have to do no installation of ROS2 at all. And they'll just directly install the container and it will start working. So although it's a straightforward and very flexible solution, but again, the thing for this is that you have to set up a Docker system for this. And the other thing is you have to learn about Docker, what are its different commands. You have to find the right images, create the right images and everything. This is yet again not a difficult thing to do, but the focus over here is on ROS2. So it makes us go sidetrack a little bit. So based on these 5 methods, the question now or the statement now is how do we simplify the installation of ROS2? So that we focus on the application and not on the installation. For this particular problem statement, I developed the software ros2env, which is a Visual Studio Code extension for managing ros2 environments. How the idea or the philosophy is that you can develop the code on your system. Let's say you have Visual Studio Code installed. You can write all the code on your Visual Studio Code, and you can then run the software or run the packages that you created on a Linux ROS environment. There would be dedicated environment for each project, similar to Python virtual environments. In this way, all the dependencies for certain projects are isolated with each other. And another good feature that it provides is its GUI works out of the box. So ROS comes with certain GUI software as well, like Gazebo, RWiz, which help with the development. What this ros2env allows is to the GUI will work out of the box, so you don't have to install anything. Just install ros2env. That's it. So I will now go on to the demo. In case you have any questions, just let me know. Just open the demo first. Okay. So if you're not able to, I'll just quickly explain the steps that are required to install ros2env. Although I think we can share these slides to the attendees as well, so you can follow along. And I also have a YouTube video as well, which you can follow along when you're trying this offline after this meeting. So the first step is installing Docker Desktop. For this one, what you have to do is open your browser and you just have to go on Google and type install Docker Desktop. The official Docker documentation will be the first link, and you just click on it and just follow the instructions that are given here. If you are on a Windows system or on a Mac system, anything, you can just install Docker Desktop on Windows. It's quite straightforward installation. It's just a package that will get installed. You just have to follow the on-screen instructions. Very easy. Then the next step is you have to install Visual Studio Code. Once again, this is also straightforward. You just go to Google and type install Visual Studio Code. Oh, okay. Is the video quality not good? I think it would be better now. So the next step is to install Visual Studio Code. You can just again Google this thing, install Visual Studio Code, and the first link that pops up, you can just follow the on-screen instructions for Windows or Mac system or even a Linux system to download the Visual Studio. Then the next step is installing the ros2env extension, which once you have Visual Studio installed, which will look something like this, I think most of you would be familiar with this. We will go to the extensions tab, which is somewhere like okay. So I'll try resharing my screen if there are issues with the video. Is it better now? Same thing.
Yeah, sorry, Sakshay, it's not very
Hmm.
clear just yet. And still
Yeah.
coming through.
Can,
Yeah.
can you see the text or is it also blurry?
Yeah, the text is quite blurry.
Oh, is it? Hmm.
Maybe do
What?
you have like a backup network that you can connect to?
Let me try once. Any better now?
Actually, it's still kind of the same. I think for now, I will suggest that maybe you still continue with the presentation, but it's still kind of the same. I can't really explain why also from my end here.
Hmm.
Ah,
Okay.
we'll try and follow so that I'll always
Okay.
mess up.
I have a YouTube video as well, which I'll share as well. So you can just follow along with it. Then that would be fine. Then after Visual Studio Code is installed, there is this extensions tab over here, which is, let's say, 1, 2, 3, 4, 5, 6, sixth from the top. And in there, you can search for extensions in the marketplace. Over here, you have to type ROS2ENV, ROS2ENV. So the first one will come up with my name as the developer. You can click on install the ROS2ENV and it will get installed. Then after you have installed ros2env, you just have to open Visual Studio Code and you will type and on your keyboard you just have to type or control shift P. Text bar kind of thing will open up and you can write ros2 colon. This will give up all approximately 6 commands, which are delete environment, load environment, stop environment, open GUI, create environment, and open terminal. The create environment, as I said, it will create a ROS2 environment. Once you click ROS2 create environment, it will ask for a ROS2 distribution. The current ROS2 distributions which are supported are Kilted, Rolling, Humble, Iron, and Jazzy. Now, whatever distribution that you choose, it will take certain, if you're trying this for the first time, it will take some time for it to install it from the server. After it is installed, okay. For example, I have rolling installed, so that's why I will click on create environment and I will select rolling over here. Then it will ask for a name of the environment that you want, ROS2 rolling. And then there is an advanced setting as well in case you are already experienced developing with Docker. There is a concept of ports. Now, if you want certain information to go out from your environment and into your local system, you can open certain ports. You can open certain ports, but for the default case, or if you're just new to ROS2, you can just press enter and leave it empty. This will take some time and it will open up a new console or a new window in itself. Now, in the bottom also, you will see something like active ROS2 rolling. This means that this environment is currently active now. Now, since this environment is active, the terminal will also start responding to your ROS2 commands without doing any ROS2 installation. So you type ROS2 and you will see that ROS2 is already installed on this terminal. So it's the basic ROS2 command that we have. It's just the default one. Now, let's say you want to open the GUI for the environment. Let's say you want to run RWiz on this, which is a visualization software for ROS. You will type Control Shift P ROS2 colon, and there is this command called Open GUI. You will click on it, and it will open up a new browser tab on the VS Code. You will click on Connect, and it will open up the GUI for the Ubuntu system that you have. Over here, there are some quick to use software as well already installed, like Terminator, VS Codium, all these things. Let's say you want to open RWiz, you can click on the Terminator and type in RWiz to RWiz. I think this, yeah. It just starts RWiz, which is the visualization software, and then you can do all your things in this environment. That's for it. Let's say let's say you were working on one project, let's say mobile robot project, and now you want to switch to some other project of your choice. Let's say a robot arm project. You will once again click on Control Shift P ROS2 colon, and then you can create a new environment for this. Let's say I again create a new environment. I again click on rolling, and you can type ROS2 rolling 2. This is just an arbitrary name that I'm giving. You can give any other name. Again enter, and it will load for a few minutes and open up a new ROS2 environment, which is now ROS2 rolling 2. And this is completely isolated from the previous environment that we have. So you can start your project fresh from this instance. Let's say, again, I'm going to Control Shift P. Let's say I want to stop this environment and I want to work on something else entirely. You can also stop the environment also using the Stop Environment button. Also, let's say you want to load, let's say you have done your work on the robot arm project and now you want to switch to the mobile robot project. You will select the ROS2 load environment button command. It will give you the options of what the current environments are available. So the first one that it is giving me is ROS2 rolling 2, which we just created, and ROS2 rolling, which we created earlier. It is also listing some of my previous environments which I had created, which is before this meetup. So let's say I want to switch to the another one. I will click on ROS2 rolling, and it will switch the environment to ROS2 rolling, and all these installation and everything will continue from here onwards. This command also provides a way to delete the environment also using ROS2 delete environment command. You can select which environment you want to delete, and it will completely delete everything, or all the files, every installation, everything that was there for this particular environment. So yeah, this is all for the demo. You can use this to quickly get started with ROS2. You can quickly install the environment and install all the libraries which you want for your project and get started with ROS2. So this is there, then yeah. So yeah, I know stream quality is bad, but yeah. In anyways, I have a YouTube video also, which I think I'll share this in the chat itself. You can go through it in the meanwhile, and you can also go through the slides also. So that I suppose will help you with this one. So yeah, any questions?
Yeah, thank you very much, Sakshay. Yeah, thank you very, very much for this wonderful presentation. I know that there were some issues. There are issues with the maybe video resolution. Although I cannot explain, but since there's a video tutorial and also the slide will be shared, I believe a lot of those things will be clarified. And I believe also while we're uploading the video on YouTube, it will be clear. So actually, it will be clear. So, but we are also sorry that maybe the video was not clear, but although we didn't know how to really sort the issue out yet, but we know that it will be clear when everything is being pushed out properly. Yeah, thank you once again. And I think there's a question that was pasted here. I'm trying to look for, I think the individual was asking about, okay. That is Abu Conte. He was asking a question. Please, if you have a question, please just try and drop it. At least from what you got, just try and drop it in the comment section. Yeah. So someone asked a question, said, do you have any recommendations on which computer model can best run simulations? I don't know if do you have any recommendation on which computer model can best run simulation? I don't know. I'm Abu Conte. I don't know if you are there. Can you also maybe throw more light on the question if possible? Yeah. Hello?
Okay, I'll try to answer this now.
Okay, no problem.
Yeah, so it depends on the simulation that you're trying to run. So let's say you have a very simple simulation in which you only have a mobile robot, which will just move in an empty environment. Then you can use even just a good CPU with, let's say, eight core processor, it will work perfectly. But if you have very heavy simulations, let's say you have a complete factory kind of environment which you're simulating, or hospital environment you're simulating, in those kind of simulations you would require a GPU to best see the simulation. That I would recommend. So if it's a simple simulation, even I guess computer models that are latest ones, they will very easily run simple simulations. But if these are advanced or big ones, then you'll probably need a GPU for running these kind of things.
Yeah. Thank you, Thank you, Sakshi, for the answer. I don't know if the question was well answered for you, Conte. If so, you can maybe throw a like or something. Okay, there is a ant from Mr. Sikiru. I don't know if there's any other. Let me check. Let me go around just to see if there's any other person raising up this one. Okay, there's another ant here by Elisha Okara. So I think I'm going to call Mr. Sikiru to ask his question. Then later, Mr. Elisha. Yeah, on to you, Mr. Sikiru.
Yeah. All right. Thank you, Samuel, and thanks actually for the presentation. By the way, for every other person in the meeting, we will make the video available, and I believe the stream quality issue will not actually affect the video, so we'll make it available and you can all see it. So for the ROS2 environment, I want to know, is it possible that I have different ROS distros and then still working on the same ROS2 environment at the same time?
If I understand it correctly, each ROS2 environment that you create is based on a specific distro. So if you create a ROS2 rolling distro, it will only contain a ROS2 rolling one. If you create a ROS2 Humble based environment, that it will only contain ROS2 Humble based distro. So you can create multiple environments with different distros as well. So it depends on you. Whatever you choose on the options, it will automatically create that environment.
All right, thank you. I think that answers my question. Thanks.
Yeah, thank you once again. Okay, so Stevedan has a question, but let me go to Elisha Okara. Can you ask your question? Then later Stevedan.
Yeah, hopefully this is not a silly one, but you know when you create an environment with the extension in Visual Studio, where like is there a default directory that these things pop up? Like where are they being saved?
Yeah, these are saved in your home directory. So it is different for Windows, different for a Mac system, but it's basically your home directory or your user directory, you can say, which if a Windows or a Mac system creates by default. All the files that you will write for your project, they will be stored at that location.
Okay.
So
And
if
like the
you,
extension, oh, sorry, carry on, carry on.
yeah, go on, go on, go on.
The extension when you create the environment, so like setting up all of the it's like setting up the packages and stuff. So you don't pretty much have to do any more installations. You don't have to like build anything afterward or like what's it like after you've created it and you actually want to be working with it?
Once you create a ROS2 environment, it will have the default installation for ROS2. It will have RViz installed. It will have Gazebo installed. All the basic things to get started with ROS2, call, con, and everything. But let's say if you want to work on, for example, nav2 or navigation related things, then you have to install that particular package, ROS2, nav2, Humble, or rolling like that. So the
Yeah.
basic installation or basic everything is included, but for extra things, you have to go and download or install those. But the thing is that once you install those things, it will be saved in your environment forever. So even when you stop the environment and let's say next day come and load that environment again, the installation will stay there itself. You can continue
Right.
your work from that.
Right. Okay. Yeah, that's awesome. Hey, this is fantastic, man. I think that you've done a great job here. Are you
Yeah.
maintaining this yourself?
Yeah, yes. Like I started working on it. Maintenance now is getting like I have other things to that keep coming up. So maintenance is difficult these days, but yeah, it was done earlier.
I mean, hey, I'll be happy to help out. Like if you're looking for people to collaborate, keep this open source project running, then yeah, I'm sure there'll be other people on this call as well that'll be happy to lend a hand.
Oh, sure. Yeah, it would be good if anyone would be willing to help to maintain it. There are quite a lot of open issues also, so it would be good to help.
Okay.
Yeah. Thank you very much, Mr. Elisha. And for those that want to contribute to the project, please just go to I think from the links that will be sent, you should get linked to also the GitHub project. Please just go to the GitHub discussion of the project and just start the discussion. I think there's a first issue there already, so you can try it out and try contribute to it. I think this is a good work. Yeah. Yeah. Thank you very much, Mr. Elisha.
Sorry,
There's a
Mr.
question.
Samuel, the
Yeah.
the email you sent us only has the repo for the Kalman filters, unless I'm missing something.
Okay, no problem. Sorry, we'll send the GitHub link also for Mr. Sasuke's project. Yeah, we'll send that. So yeah, thank you very much for that. Yeah.
Thank you.
So before I call Mr. Stevedan, there's a question here I just want you to on the chat. He said if you have a it's okay, let me say, does ROS2 ENV have good support for have GPU support? does ros2env have GPU support? For example, if you have a computationally expensive simulation that can be accelerated by your computer's GPU, so can ros2env do something like that? So that's the question.
Uh, for Windows, according to my knowledge, just feel free to correct me if I'm wrong on this. So Docker for Windows doesn't have really good support for GPU. So if you are running, so basically ROS2env uses Docker behind the scenes. Now, since GPU support is not very well for Docker, so Docker for Windows ROS2env doesn't have good GPU support. But let's say you have a Linux system and over there you try this, then it will have good GPU support for on a Linux system. So yeah, on Windows there is not really good support for GPU on for ROS2env.
Yeah, thank you very much. Thank you. So please, the person that asked the question, I think you try it out on Linux, can share your experience also. And so since it's an ongoing project, yeah, I think that would be good. So to Stevedan, yeah, can ask your question.
Yeah, I have a question. By the way, amazing job, because I remember when starting my robotics journey, the amount of PCs I had to install in Ubuntu because I crashed my dependencies and NVIDIA drivers and ROS Humble, ROS 1, ROS 2. It was a mess. So really, really nice job. By the way, I'm curious about, like, can I use my own Docker as a base for the ros2env? So instead of using like the Docker you create, can I use just mine?
That option is not available as of now. Right now, it uses some default image that is there, like available online. It will only set up that image itself and that container. If
Okay.
you want to use your own, that I guess would be a good issue or good enhancement to this one.
Okay.
Right now, there is no support for custom Docker. So yeah.
Okay, no problem. Thanks.
Yeah, thanks once again, Stevedan, for the question. So, like I said, like you already explained, I think the project is in development. So maybe you can also contribute to add the option for custom Docker, like that. Yeah, thank you once again, Sasuke. Although I have a question, I'm just looking at time. I just have two questions actually. Yes, well, I'm looking at time. Let me just ask it regardless. I think it will benefit people. The first one is about um, things like doing things like SSH. For example, I'm maybe communicating with a remote device. Can you do something like that? Like SSHing, communicating with remote device, like a Raspberry Pi. That's one. They also want to ask about things. How does it work? Because I noticed it was an Ubuntu interface based on your description. I've also tried. I've tested it before. I want to ask what's anything about hardware interfacing. For example, I have a LiDAR. I just want to test maybe the code, maybe the particular code was running on Humble, and I quickly want to test, will it work on Jazzy before I put it on my robot? You understand what I'm saying? I quickly set up maybe a Jazzy environment. Is it okay for something like that? Maybe for hardware tests, then SSH in remote and things like that. Yeah, that's my question.
Okay. For SSHing into the system. So for hardware, I have also not tested how it works with hardware. But for SSH, this project, this certainly you can connect with remote systems using SSH, but there are certain limitations with that, which when I tried it, although you can SSH into another system and it will work fine. You can do all the common SSH stuff, but when you do the ROS2 things using SSH, then you will face certain problems over there. For the hardware, I have not really tested how it works with hardware. So I can say how it will work. Mm, it's something that needs to be tried out.
Okay, thank you. Thank you very much for the answer. So I think that would be all for this section. But basically, so I think the summary is whether you are using a Windows. I think if you are using a Mac, I think recently I asked someone to try it on a Mac and he gave me good feedback. So if you're using a Windows or a Mac PC or even an Ubuntu PC, you need to start, you need to get started with ROS. I think this day, try this workout, try the ROS2 ENV out, and the feedback generally has been okay. So I encourage you guys to try it out. Like I said, the video will also be out. I believe that the quality will be better when the video is out. And also, Sakshay can also share the link to the presentation on the chat, and the link also to the project will be shared with you guys. So thank you once again, Sasuke. It's really an honor to have you and make this presentation. I believe a lot of people will try it out and will start getting started with their ROS2 development. Thank you once again, Sasuke.
Thank you. Thank you for inviting me. Thank you
Yeah.
for all listening. Yeah.
Thank you very much. So we'll be going to the next section, and the next section will be anchored by one of the ROS community coordinator also. His name is Mr. Sikiru Salau. So over to you, Mr. Sikiru.
Yeah, thank you, Samuel. And by the way, can everybody hear me? If you can hear me, can you give a thumbs up? All right, great. Thank you, Yusuf. All right, thank you, Uzo. So I want to believe that, yeah, I'm actually being heard. Yeah, so the next session, without wasting too much time, will be handled by Stevedan. And one of the things we are trying to do in the community actually is also to make sure that whenever we have events like this, we bring roboticists from Nigeria, because at the end of the day, this is a Nigeria thing, and we try to bring roboticists from wherever they are in the world, and then we make sure that Nigerians are there as well, so that we can kind of like promote uh, robotics people in Nigeria. And one of them is Stevedan. He also, like Sakshay, contributes to ROS2, specifically the NAV2 project. And I think he will be talking to us on some things that relates to localization, Kalman filter on ROS2. So I think from there, the floor is all yours, Mr. Steve. You can, maybe introduce yourself more. Some people may want to know, where you school or where you've schooled or something like that. What you currently do. Yeah. All right, Mr.
Okay.
Steve.
Okay. Can you guys hear me?
Yeah.
Can everyone
Good.
hear me? Okay.
Good.
So can you see my screen? I don't know if I'm sharing it correctly.
Yes, I can
You
see
can?
Yes, your screen. We can see it. We
Okay.
can see your screen.
Okay, perfect. Let's start a bit of a timer so I don't go off time. By the way, just I'm also going to introduce myself later, but this topic of common filters, I heard in the beginning of the session that most people are beginners. So I also did the implementation in C++. So I should have done it in Python, but most likely in a real situation, doing localization, you did the C++. So if you're a beginner, just if you don't understand anything, let me know. There's also a bit of concept I might throw around that if you don't understand, please ask me a question. Assuming that obviously everyone knows a some basic concept of like mathematics, derivative, and stuff like that. But yeah, if you don't understand, please let me know, and I'll stop and explain each of the concepts. And also, I tried as much as possible to find the middle point, not to go too advanced because obviously it doesn't make any sense, and not to go too easy, but find the point in which that at least you can understand the concept. In the end, you can always look at the code and implement it yourself, or there are a lot of implementation of common filters in ROS ecosystem. Most likely, if you have a robot, you won't implement from scratch a common filter. You just use the robot localization common filter. So this is the main objective for you. I want to understand the concept of common filters. Okay, so let's go to the next. Okay, so just a bit of background on who I am. I'm Nigerian, also Spanish also. I have a bachelor's in mechanical engineering and also a master's in automatic control and robotics. I have basically more or less an experience of, let's say, 3-4 years, 4 years in industrial experience and 1-2 years as a research. I've worked with like a lot of robots, well, from robotic arms to drones. My previous company, for example, now I work more in vision beam picking or defect detection, for example. So now I do more control, more, let's say, vision-based systems. And also, which I will talk about this in the end of the session, is I also do a lot of contribution when I have time to open source projects. I always do recommend people to do it, especially when you have time, because the more older you get, the less time you have. So now that you can, just do it. Trust me, it helps a lot because you do learn a lot of things at the same time. So I would recommend you do that. Before we start, I sent Sikiru sent like a README in the repo, which explains how to install basically the setup for today. I'll go to do like a quick, like a 2 minutes quick recap on how to do installation. I'm using Docker, by the way, because the issue of what my previous presenter said before, of having different machines and having different dependencies is a mess. So Docker just simplifies that a lot. So I'm going to share my, so I don't know if you guys can see my screen. So basically, I'm going to do like a quick setup to set up your environment for this demo. So I do this in Linux. You can obviously also do this in the Linux in Windows. I would not recommend to use Windows. I have not tried this in Windows. I don't use Windows for more robotics development. I would recommend Linux. And I'm assuming that you guys already installed Docker, which is what was explained also in the README. So the idea is to first open your terminal. In this case, I'm just following the README I placed in the repo. So this one, I don't know if you guys can see the repo. Please, can someone confirm you can see the repo? I'm sure. Can you guys confirm it?
Yep.
Yes.
Yeah, we can see.
Okay,
Yes.
perfect.
I can see.
So perfect. So the idea is that basically, obviously you should install Docker, which I assume you have installed, and also I created an image which have like almost everything you need installed, so you can just pull it. So I already have this in my PC anyway, so I don't need to pull it again. And this is, those that work with Docker will understand what this is. See, so that you can have GU applications from inside Docker in your main system. So you just run that, and also so you need to also clone the repo. So git clone it. I already have it cloned. So this is where we have this over here. So I already have this cloned in my Visual Studio environment. So I will advise you to clone it. And we also run this command. Okay, so this command, what it does is basically it opens the Docker, mounting the repo inside the Docker. So that's why you have to obviously change the path to the repo locally. So change the path to where you have this installed locally, and this should mount it inside the Docker. So in my case, I also already had this. So Docker run. Okay, so by the way, be careful with this. So this, you can see there's two localization. This is the main repo. So this basically is the reason why this is done like this is because if you notice, I have basically two folders that's called location KF. You want to mount the second one, just so you're aware of this. So the mounting you put is this location basically. For all this will be this location. From this to this is basically this location. So
I'm sorry,
okay,
Steve.
tell me.
I just wanted to interrupt for a second. Is it okay if you slow down a bit, because the video
Okay.
is got like a 1 second lag, so sometimes
Okay.
when what we see and what you're saying are not like in sync, you know?
Okay. Thank you for saying that. Thank you. Okay, I'll try to go as slow as possible. Okay, so I don't know where was the last place that you saw me where I think you understood this, right? To open the Docker.
I'd say maybe
Yes?
just go back to like step 4, running the container terminal.
Okay. So in order to run let's go back. In order to run the container, you have to run this command. So the docker run command. It's a lot of commands, but you don't have to worry too much about everything. All you have to worry about is just this specific line. So basically copy this into a txt file, or any way you see fit. For example, let's do it here. And all you have to do is, after cloning the after cloning the location of, after cloning the repo locally, you need to copy, you need to go inside the second level of the localization and copy, find this location, put it in this path from here to here, and then run this command. So what this does is basically it enters the Docker and it also mounts your local file inside the Docker. So this way, if you make changes, it shows in the Docker. This, I'm assuming you have a bit of knowledge in Docker, so you don't exactly have to have a knowledge, but you should have a bit of basic knowledge in Docker. Okay. So with respect to the repo, there are two branches. There's one that's called main, and the other one called exercise. The main has the full solution. So, and the exercise has some partial written codes that at some point, if we have time, you can fill it and fill it up, and this way you can understand better implementation of Kalman filter, because the best way to understand something is by implementing it. So I did put some to-dos in the code that you can look into it and see if you understand what I explained, and you can look at the code and finish it. Obviously, looking at the solution, which is main, which is over here. So I would recommend to go to the exercise branch and then mount it and go inside the Docker. So in this case, enter Docker, and in another, as I said in the README, also you can launch the simulation. So this is basically a drone simulation, an empty drone. So source your environment as always. I always forget that, and then you can launch the drone simulation. So and what this does is just launch a gazebo environment with the drone in the middle. So just a simple simulation, nothing much. And also, we open a different terminal. The same Docker, we also source it. And in this case, you could run the bring up, which what this does is brings up the solution. So a lot of things shows up here. So I have RVs. What this basically does is it allows you to do like predefined trajectories. So I did it so it's easy for us to test the Kalman filter. So in this case, I have 3 different trajectories, so square, circle, and figure. So in this case, what you have to do is just to, like, for example, start navigation. And what this does is just does a square trajectory. That's all. This is basically just a simple navigator code that just does simple trajectories. It helps a lot just to test the Kalman filter. As you can see, it just does a square trajectory and it just does this. And you have also the circle and figure 8. Also, lastly, for those that work with robotic system, you know, plotting helps a lot. I also recommend also to use, in order to see the way your system behaves, is to use plot juggler. So what plot juggler is, it's basically a way to visualize the data of your system. So this already installed in the Docker. So all you have to do is just run this, and this opens plot juggler. Plot juggler in this case has a lot of tools for you to visualize the state of your system. So for example, let's see the estimated, for example. In this case, we could see and open more chats. Wait, yeah, because it's not started yet. Yeah, because I'm using. Okay, sorry, let's use a different one. Let's say ground truth. Let's say this. So we can actually see the state of our system. This helps a lot because you can see how your system is behaving, and it does helps a lot, especially for tuning controllers, for those that work with controllers. So this, for example, an example. We'll go to this later. I just a quick recap on how to run the code. I think this if you have any question, we'll go to this later. So I'm going to shut this down. You can test it if you have time to do this. You can always test this. Okay, back to the presentation. Let me see the time. Okay, so before I start, I'm going to explain a bit of what are we trying to solve. For everyone that worked in autonomous system, the whole idea of autonomous system is you have like a decision maker that tells the robot, hey, do this. In the lower level, you have a planner that says, hey, that defines the set of points the robot has to go in order to do what the decision maker said. And most likely in the lower level, you have a controller. It can either be a PID controller or MPC controller. And in order for the PID controller to adjust correctly and tell you the next actions for you to go, you need to know where you are with respect to the world. So the main objective of this talk is to how do we know where we are with respect to a world system. What I mean world system, I mean like, let's say outdoor, even indoor, using a map, the multiple system or frame of references. So in this case, we're going to focus on outdoor drones because that's what I have experience with. But in the end, the algorithm is kind of the same. It kind of works the same because localization, it's in the end, it's just fusing data sources. So it works also for indoor and it also works for outdoor also. Now, the problem is like now, how do I, give me a sec, I think there's, give me a sec. Sensor. Okay, so yes, go ahead. So if you have any question, please stop me. If I'm going too fast, also please stop me. I do sometimes talk way too fast. So now the problem is, how do we estimate the state of our system? Because nowadays there isn't actually a sensor that gives you, when I mean the state of a system, I mean my XYZ, my velocity, my angular velocity, and my orientation, just so we're a bit of in the same page. So the idea is that how do I get the state of my system with respect to a reference frame? Currently, there are solutions, obviously. There isn't exactly a sensor that gives you all the states of your system. There are sensors that came out quite recently that use actually sensor fusion algorithms like Kalman filter to estimate the state of a system. But there isn't actually a sensor that gives you, hey, this is the position you are with respect to, well, there are, but there isn't the one that gives you a full state of your system. So what do? You say, okay, what you think of, what if I combine different sensors? You can say, okay, I have like different type of sensors. I want to, with those sensors, estimate where I am with respect to a reference system. So in this case, as I said, we're going to focus on outdoor drones, and the idea is to try to estimate where I am with respect to the world frame. Now, how do we do that? So we select a set of sensors. One of the first obvious sensor that we can use is EMO. I don't know if you guys know what an EMO is. An EMO, basically what it does is it tells you your acceleration and your angular velocity with respect to the body of the EMOs. So this way you can know how fast you are going. And the good thing with EMO is you can actually get your position and velocity from that data. You can say, okay, I'm going this certain acceleration. I can integrate my acceleration and get the velocity, and with the velocity, get the position. What I mean by that is that, for example, the simple equation that we all know from primary school, so which is velocity is equals to initial velocity plus acceleration times time, which is you can use that. So you get the acceleration from the gyroscope. Dead reckoning is basically what I'm saying, is basically you do integration to get velocity and position. That's what dead reckoning is. So you say, okay, I have acceleration from the EMO. And what I do is I use the integration to get the velocity, and I use also the integration of velocity to get the position. So that's simple. And one of the advantages of this kind of sensors is it's quite fast frequency. I don't know if you guys have worked with controller, but controller, at least you need to work at 30, 50 hertz. So you want something that gives you fast update of the state of your system. But if not, if your state estimation is too slow, then you have the problem that you react way too slow. So you are basically reacting or controlling based on old data. But the issue with obtaining the position and velocity just from EMO is something called drift. So just let's see a situation. Let's look at this picture down here. This one called traveling blind. Let's imagine that you are at the door of your house and you are blindfolded and you are told to keep walking at random directions and stop. Now imagine we start at a point A and you go straight. What's the likelihood of you actually being at the point you assume you are? It's quite difficult because you're it's basically like traveling blindly. You are just going and trying to estimate your position randomly based on your state. So that's why one of the issues with just using EMO for state estimation is you get a lot of drift. So like the robot starts at this point and you estimate, you say, okay, this is my acceleration, this is my current position. I estimate the next position. There's a possibility that your reposition can actually be slightly offset, but you don't know. So what people noticed and start doing is they start combining different sensors. So you take advantage of different sensors. Like, okay, so we know that EMU is quite fast. So you use EMU for like, you can use EMU for iteration, but also you can also use, I think it's the other way around. So I noticed I made a mistake. So I think I already explained this, but it should go back. Also, you can also use a GPS. One of the good things of GPS is you get like a really quite good position of where you are with respect to hertz, and it's less drifty like the EMU sensor. So you can get you know where you are with respect to, for example, in this case, the Earth. But one of the disadvantages of GPS, or just using GPS for control, is it's quite low frequency. So that means you get your data quite slow, and this is not good for your controller, because if your data is slow, you react slow. So the idea is, just so you guys are understanding me, the idea is we want to look at multiple sensors, take advantage of the strength of these sensors, and combine them together to get a really good estimate of our system. That's just the gist of what I'm explaining of each of the sensors. In the case of EMU, you get the fast frequencies, fast update rate, and also in the state of GPS, you get slow update rate, but quite good estimation of where you are with respect to the world. Okay, another one is the magnetometer. Basically, what this does is it measures the magnetic field with respect to Earth, or magnetic field of the sensors. And the good thing about this is you can use this to estimate the heading of where we are with respect to the we can estimate, for example, whether we are 0 degree with respect to east or west, which is quite good. But the issue with those kind of sensors is if you get so close to another stronger magnetic field, your sensor reading might be bad. So it's kind of a bit of a caveat. So, and the end is the same. You tend to find the strength of each sensors and tend to compensate it with the weakness of other sensors. I won't include this in the explanation either, but one also widely used sensor is cameras, which basically with the camera you can estimate the change of position. So I don't know if you guys know of VIO algorithms. So what the visual inertia odometry does is it tries to estimate the velocity and acceleration and position of a system just using cameras. This is also one technique also used. I think I'm missing one here. I think one also option is using, for example, a barometer. I don't know if you guys know what a barometer is. So you can measure the altitude, a change of altitude of your system. So you can know at this specific time I'm at this specific altitude pressure, and you can, based on that, you can estimate the difference in altitude. So now, how does come now? What's the strategy now? The strategy we know is that we have different sensors. So now we want to try to take advantage of each of the sensors. So we take advantage of the fast nature of some sensors, of the correctness of some sensors, to join it together. So the idea is, like, remember the example I said in the beginning, walking blindly. So it's the same. Now you have a different strategy. For example, you start in the door of your house. You start walking blindly. After every 10 seconds, you're allowed to open your eyes. So after you open your eyes, you adjust your system. Say, oh yeah, I'm in this position in my house. What if I adjust a bit? You close your eyes again and you keep going with the email. You do the same. You open your eye a bit and you adjust. Hey, I have a reference. So I know where my house is. So it's basically the same idea. The idea is we combine different sensors and we combine different sensors in order to enhance our state estimation. Now, the question is, how do we do it? Now, this is where I'm going to enter a bit of Kalman filters. I'm going to give a bit summary on Kalman filters. I'm not going to depth because you can also search this online anyways, but Kalman filters is basically a specific case of a bias filter. A bias filter, the idea is you try to estimate the state of a system. And basically the whole idea is you have two steps. You try to predict where the system is. So let's assume that you have a model of your system. You know how your system behaves. You know that, okay, given a set of inputs, my system is going to output a specific set of outputs. So you can say, on the first stage, you can say, okay, this is my current state. I can not guess, but I can estimate the next state of my system with my system model. And in the next stage, you correct your system. So as I said before, imagine you are blinded and you're at the door of your house, and every 10 seconds you're allowed to walk, to open your eyes. So it's the same. So every time step, or every certain of time you get a new measurement, you correct the system state. You say, okay, I can open my eye now. I can kind of correct where I am with respect to my, for example, my house. There's an example of that. So, okay, so now, but a good illustration of this is given what I knew before and what I sense now, where am I likely to be? So that's basically the whole idea, is that you know where you were before. You can kind of guess where you are next using the state model of your system. And also when you get a new measurement, you can also kind of adjust yourself to know where your next state would be. Now we're going to go into a Kalman filters. Kalman filter is basically a bias filter.
Sorry,
but
Steve, I have
assume
a
that
question.
Tell me.
In this example, are we also sort of like, what's the word? Like fine-tuning our, like perhaps this algorithm that we're using to predict. So just as
Yeah.
much as I'm wondering, just as much as we're trying to course correct and say, okay, like this was
Yeah.
my objective, this is how far
Yeah.
I actually am from that in this state. Are we also saying, okay, so are we let's fine-tune what we're using to calculate or predict next state so that we're more accurate each time?
Kind of, yes. So that do this have to so the idea is what I want to explain what the Kalman filter does. So what the Kalman filter does is that you give it like the noise of your system. So like you give it the noise of your prediction model. So you have a model that estimates the next state, but you also give it what is the likelihood of this prediction being bad. And also in the correction stage, also for each sensors, you give it also this data. You give it, it's called the covariance matrix. It kind of tells you how bad is your measurement, kind of. So what Kalman filter does is, based on how bad your measurement is, it trusts one source or the other. I don't know if you understand what I mean. So like you say, okay, I have the covariance of my prediction model. I have the covariance. Covariance, when I mean covariance, I mean how your system deviates with respect to the mean. And what the Kalman filter does is, based on at every time step, it decides, okay, the covariance of this system is worse, so I'll trust my prediction more. Or the next stage, I say, okay, the covariance of my measurement is quite good, so I'll trust my measurement more, and I'll give more weight to my measurement in order to update the state system. And if you understand what I mean.
Yeah.
So that's what the Kalman filter does. It does the fine tuning inherently, because you do pass it the noise of your system, of both the sensors and both the prediction model. So if you have any question, please also stop me. For now, I'll continue. Tell me.
Yeah, I think I want to just give a small instruction here. Because of our time frame, I think it's more important that the speaker actually finish his session, and then from there we can ask questions. Because if we keep asking questions, he might not finish the session within the time frame. So whatever question you have, kindly note them down or type them in the chat section. And then when it comes to the Q&A session, we will actually take the questions. But let's focus on the session itself right now, because the video actually will be available later, and then you can go over it again if you missed any point. So ask the question later at the end of the session. All right, Mr. Steve, you can go ahead.
Thank you. Also, okay, now, as I said, the Kalman filter is a specific case of the bias filter. The difference is the Kalman filter is just assumed that everything is Gaussian. When I mean Gaussian, I mean that it assumes that the evolution of your state follows a Gaussian style behavior. So when I move a specific time step, I know that it's a possibility that my state would be at a specific mean deviated at that standard deviation. That's basically the idea of a Kalman filter. And in the case of a Kalman filter, there are two different, well, no, there are more obviously, but I want to focus on mostly one, which is the extended Kalman filter. The extended Kalman filter is a specific case of a Kalman filter, but assuming that your system is nonlinear. And if you guys have worked with a nonlinear system, most likely anyone remembers the cosinus that hides in the middle of your matrix. If your system has a cosinus, most likely it's a nonlinear system. And there's also another case also of a Kalman filter, which is called the centered Kalman filter. It's comparison, just so you guys, I think if you guys have worked with the robot localization package, you would have seen these two algorithms. And in order to choose which is best, I'll just give a bit of advice. Most drone software like Autopilot and PX4 use external Kalman filter. Why? Because external Kalman filter is less accurate, which is true compared to UKF, but it's way more computational efficient. So what you gain from the accuracy is not worth it, because most likely when you're working with drones, computation is quite important. But also UKF is quite work well. UKF also what it does is that it tries to estimate. The idea is that they try to estimate the non-linearity of your system because you can't just get it easily. So extended Kalman filter uses Jacobians. I don't know if you guys know what Jacobians is. And extended Kalman filter uses like a particle filter to estimate the non-linearity of your system. So that's the difference. The idea is how do I try to guess the non-linearity of my system? That's the difference between the two algorithms. But most likely, if you're working in drones, you most likely use an EKF. If you have mobile robots that has way more compute, you might also use UKF. Extended Kalman filter. I'll go fast because it's a lot of equations, but they're quite trivial. I won't go to the equations because you can find them online, so it doesn't make any sense. But what I will do is explain how to create the problem of a Kalman filter, of a extended Kalman filter, how to define the problem. This is way important than actually the equations because it's always the same. Trust me. There's a slight difference, but it's always the same. It just matters of operations. So, see, as I said before, a Kalman filter is a bias filter. You have two steps: the prediction step and the update step. The difference is that the extended Kalman filter kind of estimates the change of the system using Jacobians. So because you can't exactly find, because in the case of a linear system, I don't know if you guys remember the representation in controls. The good thing about of a linear system is you can obtain this A matrix quite easily. So that's basically your Jacobian. But in non-linear system, it's not that straightforward. So you need to use a different techniques, which you use the Jacobians, which is partial derivatives. If you understand what I mean, please let me know. Then we can talk to this about this later. Also, and as I explained before, the question the previous person asked, each of the system has noise. You have to tell the Kalman filter how good you trust your model or how good you trust your sensors. And so based on this, the Kalman filter tries to adjust your estimation based on these covariances. As I said here, so it basically trusts one input or the other based on these covariances. And also, this is also a minor change I used on, well, I used like a specific implementation of the extended Kalman filter using the Joseph form. You can look it up. I won't going to explain that because I don't think it's worth me explaining. I think the concept is more important than actually going to the specific matrix operations. So I want to explain the most important thing in Kalman filters or extended Kalman filters is from the process side. When I mean the process side, I mean the prediction side, is your state transition function. So when I mean state transition function, I mean this x is equals to ax plus by, how your system evolves in time. That's basically what that means. Your Jacobians, which tells you how your system changes in time. So it's basically, in this case, it's the partial derivatives. And also you need the process noise, which is really painful to tune. This is one of the most painful parts in Kalman filters. And also from the measurement side, you also need nonlinear measurements function. Basically what this does, it says, we'll go to an example now, so you guys can understand what I mean by this. It basically tells you how your sensor translates to the states. We're going to go to a simple example so everyone can understand. And also the Jacobian is basically the same. It's the derivative of that matrix with respect to state. Finally, also the covariance, the noise covariance, which most sensor gives you that data. So you can get that from the sensor directly. So let's go to a 1D example, which is, I think this is what I was taught the first day I learned about Kalman filters, and I think it helps a lot. So let's assume we have a drone in space. I want to estimate the Z of the drone and the velocity in the Z position. Now, how do we do that? Let's assume also we have just one sensor, which is the range sensor. A range sensor basically tells you how far you are from the ground. And also, we are controlling the drone with remote control. So we know the accelerations we're sending to the robot. So the idea is now, the problem is, okay, we have a range sensor and we have a control input. How do we estimate the state of the system? So let's define the problem. So we define the state, which is the altitude of the robot and the velocity in the Z position of the robots. Just a simple system. And then we'll go into the more complex 3D estimation. And also we have the control. To do this, I also actually prepared SimPy because, yeah, I left university like 3-4 years and doing derivation manually is a pain. So I don't do that manually. But if you can also do it. I would not recommend it because it's a pain and you can make mistakes. So just use something that works. I don't know if you guys can see my screen, my VS Code, or should I make it bigger?
Yeah, it's clear. I can see it.
Perfect. So we'll go to the definition of the problem. So the idea is we want to define, as I said, the transition, these matrices. So the state transition function, our system evolves in time with the Jacobians, the process noise. this I won't show you. This is just basically, I'll show you, for example, an example of this. This, in the case of our Kalman filter, it's in these params. So you can, this is, for example, the covariance of our system. And also, we want to define also the nonlinear measurement function of our range sensor and the Jacobian with respect to states. So let's go to the SymPy. I would not recommend you to do it by hand. It's unnecessary, but you can also do it faster with Python script.
Hello.
Okay, so
Stevedan.
tell me.
Can you make the VS Code font bigger a little, just
Okay.
because of maybe some people with eye problem?
Okay, zoom out. Make it a bit bigger. I think this should be big enough, if I'm not mistaken.
Yeah, just one more step.
One more. What about now?
Oh, no. This is actually big. Yeah, sorry.
So I did, but you guys can see the old
Yeah,
code,
it's
right?
good. It's good.
It's perfect.
Yeah,
Then.
it's good.
Then it's perfect. Okay, so as I said, we're going to define the state of our system. So it's the altitude and the speed of the robot in the z-axis. So our state vector is z and vx, straightforward. Give me a sec. Let me open the terminal. Open terminal. So we're going to do it is manually. Scripts 1D. So this is this is our state. Okay, and we have the controls, which is the control input of our system, which is just the acceleration in the z-axis, which is what we get from the remote control. So now we can define the transition model. And the transition model, basically what it says, it tells us, given the current state of a system, what will be the most probably the next state. And in this case, I just use the simple Euler integration, first order integration, to estimate the position based on the velocity. So you guys remember, velocity position is equals to previous position plus velocity times time. It's straightforward, and also the velocity also is equals to velocity times acceleration times time. So this is, so if I'm a specific state, I can know what is my next state of my system just using this equation. This is for example, this is a Kalman filter actually, because the system is linear. So this is actually a Kalman filter. This is not a external Kalman filter, but you can also use the same computation. The only difference is whether it's non-linear or linear. And the Jacobians, obviously, I use the PySim. You can use it manually, but I would not recommend that, as I said. And this is, for example, the Jacobian system. It tells us at every time stage how our system changes with respect to the previous state. That's quite straightforward. And also, we go to the range sensor. As I said, for the measurement model, you need to obtain the relationship between your measured state and the system state. In this case, we measure directly the altitude, so that means that it's a one-to-one mapping. So the state we measured is the Z state. So that's why you will have Z here. Basically, what this tells you is that the state we mentioned is directly the state of our system. So this is the H matrix. That's what I mean by the measurement matrix. And the Jacobian, also, as I said, it's calculated automatically. And this is what this basically tells us. It tells us that the change, our sensor measurement changes, basically. So I hope that's clear. I think in order to understand the next step, you should understand this quite well, because the next step is the same, but with a lot of states. Not too much of state, because I don't want to go too far, but it has way more states. But basically, it's the same idea. So just a bit of summary. We have our state. We have also our state vector. We have our control. And we have a state matrix that explains how our system changes with respect to time. Computer Jacobian, obviously. And we have also the measurement model for the range sensor, which is one-to-one mapping, and also the Jacobians of that measurement model. So now we go to the next complication, which is the 3D case. And obviously, I didn't put a full state estimation, like a full state, because it's a lot. You can have states that's up to 23 states, for example, which I don't think is necessary. So in this specific implementation, what I did was I defined it as following. I defined this state. So this is what I want to estimate. I want to estimate my XYZ. Everyone knows that. My velocity XYZ also. My rho, pitch, and yaw, and my angular rotation, which is P, Q, and R. Now, there are multiple strategies to actually do this. For example, in the case of robot localization, I don't know if you guys have looked at the robot localization. What they do is that they use all sensor measurements for the correction stage. So remember, we have a predict stage and you have a correction stage. And what they do is they use the control input from your controller to use it to predict the next state. So let's say you have a controller that gives you a velocity command. So what robot localization does is they take that velocity command, put it into your state transition function, and try to estimate the next state. I did something a bit different, which is quite done a lot in especially aircraft systems, is I use the emo to predict my state. So when I get the data from the emo, I use that, like the acceleration and angular velocity, to get the next state using my state transition function, obviously. And I use the other sensors to update my state, to correct my measurements. Which is the best? Depends. Like, I think the different strategies, I think mostly for aircraft, this is what is mostly done. If you look at the literature, I think I read the article that said using, for example, the using emo as a measurement gives better results. But this is a specific strategy. Use a strategy that works for you. And in the case of consideration, most likely when working with especially aircraft, you don't necessarily use roll, pitch, and yaw, because I don't know if anyone is aware of deadlocks or gimbal lock. It's basically when two axes align and you lose 1 degree of freedom. When this happens a lot when working with like Euler's angles, which is roll, pitch, and yaw. So most implementation of Kalman filter for aircraft use quaternions. I didn't want to use it because it was yet less intuitive, but it's kind of the same. Well, no, it's kind of the same. It has a specific equation, but the idea is the same. So the idea of this presentation is just to understand defining your problem, because the implementation of Kalman filter is trivial. And also, one thing also that's also done also is you include the bias in the state estimation. So what that means is you try to estimate the bias of your system, how bad your system is. Basically your acceleration bias and your angular velocity bias. So these are, if you look at, for example, robot localization, Ardo pilot implementation, or PS4, most of them you include the bias of the acceleration and I don't think robot localization does that. I know Ardo pilot and PS4 does that also, but that's also a way to enhance the state of a system. So just also recap. In this case, we use the emo. When we get the emo data, we update, predict our state with the emo, and also when we get the GPS, mag, and altimeter, which is same as barometer, we update the state. We update the state or correct the state. Same idea. So I'm going to give also. I also created a Python script also for this. It's also in the repo, so you can look at it also if you want to understand it. But it's kind of the same idea as I said with the 1D, but it's just way a lot of vectors. It's just the same idea. So as I said before, can you guys see my screen now? I don't know if you can see it now. Is it good?
Yes, we can.
Perfect. So in this case, we have a state symbol. Our state is XYZ, velocity also, and orientation and angular body rate. Same thing. So our state vector is then this. The most important thing here is trying to define the problem, because I'm telling you the implementation is trivial. So now we have a control vector. And the control vector in this case, we have the acceleration in body frame, which is what we get from the emo, and also the angular rates that we get from the emo. So now we create the control vector. This matrix, don't worry too much about it, but basically it's a rotation matrix from body to ground or to world frame. So you're given a measurement in body frame. What is that measurement in your ground frame? You can look into this. It's a well-known equation. And also this is the same also. What this does is like a transformation matrix that transform Euler angle rate from body to world frame. Okay, so let's start now. The first question is the same. Let's define the state transition function. So, this way I use a simple first order approximation. So in this case, the position is, as I said before, the previous position plus the previous velocity times time. In most cases, what you can also do is you can also include the acceleration also. So the typical position plus velocity plus acceleration, which is half times acceleration times time to the square. But I just went for simplicity in this case. The velocity update is, as I said, the velocity in previous time plus acceleration in the world frame, which what I do is basically transform the acceleration in body multiplying by the rotation matrix to get the acceleration in world frame. I also get the velocity in world frame. This is wrong. This should be in body frame. I'm using the world frame in everything, actually. And also similar to Euler angles is the orientation you have now is the previous orientation plus the orientation, the angular rotation times time, and the angular rate is basically the same as the control. There are obviously more better state transition function, that works also. So you can also try that also. This is the same as before. I automatically compute the Jacobian matrix. It's quite huge, so that's why I didn't actually bother to show it. But you can actually look into it. It's really huge. So it's this. So it's a lot of well, I mean, I have a visual. Yeah, I might have a bit of issue. Give me a sec. Maybe I might have a bit of issue, but anyways, I'll look into it later because there's no time. So just to go a bit fast. Okay, so now we create the measurement models for each of the sensors, similar as I did with the rate sensor. In the case of the GPS, we get latitude, altitude, and longitude. And with that, using either, there are actually two strategies for this. Either use the UTM or the way to estimate your position with respect to like the change of position with respect to initial position in GPS state in using GPS. So you can either use the EKF or the UTM. I prefer the ECEF because I think one of the issues I noticed with UTM is that if you guys know what UTM, if you guys have worked with this, is that when you're close to the border, it kind of breaks. So I'm not a fan of that, but I most likely use the ECEF. It's a specific way to estimate how far you have gone or the distance between 2 points in the word frame. Okay, there we go. And yeah, same. So in this case, you can, with the GPS, you can get X, Y, Z. So with respect to home position, so you define a home position, and you can using either EKF or UTM, you can get the position with respect to the home position. So it's one-to-one mapping, as I said before. So your X is the state you get in your X is the same as the state your state estimate. So that's a one-to-one mapping, similar to the range sensor. That's why the measurement model is direct. So this is mapping directly to this. And same, also you calculate the Jacobians. So everything's the same. Now let's go to the mag. The mag gives you the heading of your robot with respect to the word frame. So you can get the phi. The mag sensor doesn't directly give you this value. You kind of get, I had this implemented, but what you get is you get the magnetic field of the hertz, and for that you estimate the heading. You can look at the code. I'm not going to go into the equation, but you can look at the code fast to understand. I think it's implemented here. Mag callback. Let me see if I can find this. Yeah, this one. Yeah, you can see, for example, I compute the mag heading. You can look into the specific code to understand how I did this, but there's a specific equation that actually calculates the heading of your system with respect to the word frame in this case. Okay, so let's go back to the other case, EKF. And yeah, so in this case, the mapping also, as I said, the measurement model is a one-to-one also, but it's a one-to-one, but for the your measurement. So your measurement model is equals to the phi because it's a one-to-one mapping to the phi. Similar to this, like what you get in your state is exactly the same as your state estimate. In this case, it doesn't have to be the same. So just be careful. It does not have to be the same. But this was a simple case. Like you can see that it's the same. And then lastly, we want to work with altimeters, which basically gives you vertical velocity and also change in position. Same idea. We get the Z barometer and the VZ barometer. What we do is we define our measurement model, which is a one-to-one mapping to also to a state estimate of Z and Vx, which was explained earlier, and you get the Jacobians. And for each sensor, you define your measurement model. For in the case of VIO, for example, if you have a camera that gives you, I think RealSense does that. So if you have a camera that gives you X, Y, Z, Vx, Vy, Vz, it will be the same idea. So you get like a Vx VIO, a Vx VIO, same thing Vy VIO, and Vz VIO, which is equal to this. And the mapping is also one-to-one mapping also because because obviously if you define a non-position, so let's be careful. And this is also same. It's a one-to-one mapping, which also gives you X, Y, Z, Vx, Vy, Vz. And if you guys understand, I hope this is clear. It's very important to know how to define the problem because, as I said, the implementation is the same. If you can define properly the problem, then the implementation should be trivial.
Yeah, so I think we have 10 minutes left.
Yeah, I've seen that.
Okay.
So I'm going to go as fast as possible. I think it's finished now. So I'm going to. I think the code, you guys should look into it. There are a lot of to-dos in the code. I advise you guys to look at the implementation. But the whole idea is with the implementation is what I do is the strategy here is that I have different callbacks, so ROS callbacks. As I get the sensor, I store it in a buffer, a FIFO buffer, and I have a loop that when I get to the loop, I predict and correct all the states I've collected until that time. So in this case, I'll just go it fast in the code so you can understand what I mean by this. So in this case, I have the main loop, which is called the timer callback. That basically what this does is here we go, process control buffer and measurement time. And what this does is basically it loops in the buffer until the time. I loop until the time, now until the current time. And I do the prediction of all the sensor data I got until that time. Same as the other one. Okay, so how many time do I have left?
Yeah, you have 7 minutes.
Okay, so I don't think we have time to do implementation, but yeah. So the idea is this, and what I do recommend you guys to do. I already showed you how to launch the software. I would recommend you guys, because I won't be able to implement it now, anyways. I would recommend you guys to go to the EKF CPP. Most of the thing is there, and what you have to do is define the measurement models. I think this is quite important. So you have to define the measurement model for the GPS, the measurement model for the Jacobians also. We already got this obviously before with the Python script. Define the this also for the magnetometer also, and the Jacobians for all the sensors. I think something that is an exercise you guys should do. If you know C++, you can look at the example, the solution, and after you're done with the implementing this, also there's another to do also which I also would recommend you guys to do, which is the state function. Defining the state function. So this is state function. So in this case, what I explained in the Python script, you should implement it, like advance the states. So you're giving the current state, advance the state in the next time step. It's quite straightforward. It's just matrix multiplications. They're just one-liners, so it shouldn't be difficult. I would recommend you do it, or if you can also update the code and improve it as much as you see fit. And after you do that, you can use directly the Docker file because I already have a working solution. After you do this to do and this one and the other one, you can easily compile the code with I'll put this up. I'll update the repos to include this with the Colkin build merge install. This compiles the code. For those that are new with ROS, let me know. I'll see whether I can explain this, how to do this, if you're really interested in learning how to implement this. And that's basically all. Since we don't have time, I won't be able to actually explain this well, but let me see whether I can run a quick demo on this. Well, it's going to be difficult because of time frame, but let's see. I don't really need to bounce this at all. So let's just run this directly and see if the launch px1 same px1 launch docker let's to launch localization yeah yep bring up and py okay and lastly plot juggler. Okay, so let's do a quick demo of a working solution. Let's see, for example, the estimated and the element truth. Let's see why let me see why is it not showing. Yeah, one sec. Okay, here we go. I will go. Okay. So we do the pose. This is my estimate. And this is the ground truth. In simulation, obviously you can do this, but in real life, you don't actually have a ground truth. So yeah, that's why it's good to work with simulations, because you can tune your algorithm quite faster. So let's do like a square trajectory. So in this case, the robot goes up. Let's see. Let's do the robot starts. It takes off. So as you can see, for example, this is my estimate, and this is the this is the estimate, and this is the ground truth. So you can see how quite close is it. Obviously, you have a little of sound, but you have a bit of error. But the error is between 0.0, 0.0, which is quite small. So you can see in this case also with the x value, you can see quite how close the estimate is to the real value. So for example, this is a working example of the state estimation. Please do this. Look at it. Look at the code. Understand the code. If you see any bugs, let me know. Similar to the raw picture, orientation, and the roll, the pitch to 0, and the yaw. So look at this. As you can see, obviously the yaw, yeah, it's a bit like, that's why I would recommend to use quaternions. But anyways, so as you can see, at least the position is quite exact. Position is quite exact. So there's a lot of wind. So there's a lot of wind. Okay, so I'm going to close this. I'm going to close this. Please do it on your own. Try it out. Look at the implementation to really understand the implementation. But if you at least understand the concept of defining the problem, it should be easy. I think that's what's more difficult about understanding Kalman filters. Okay, a lot of improvements that you can do.
Hello. By the way, can anybody hear me?
Yeah, I can hear you. Sorry, I had to close my window because it's really windy. Okay,
so
I'm going to give you a bit of improvement that you can do in case you do end up implementing the Kalman filters. The sensor matters a lot. For example, in my previous company, we worked with multi-robot control. So we worked with DJI and PH4, and DJI was really solid, to be honest, and it saved a lot of headaches. A lot of drones we used the PX4. The issue was the state estimation was quite bad, so we had to do like extra work. The sensors was also quite bad, so I would recommend to get good sensors. That helps a lot, and also GPS. So now I don't know if you guys are aware of LTKs. They also work quite well because we also did position landing, and we did state estimation while doing position landing, and we noticed that network RTK worked also quite well. Network RTK is the same as mobile RTK. Basically, it's something that you have to put close to the robots, but the difference is that you don't require hardware, because the issue with having a mobile system RTK is the hardware, leaving the hardware outside for a long period of time is most likely not a good idea. So network RTK did work quite well. Obviously, use quaternions, also model your sensor bias. There are also techniques also like distant gating. You can look this up, and you can also include the bias and also the VIO. I think there's some stuff repeated, doubled here. Finally, I think that should be Kalman filter. I apologize if it's a lot of things at the same time, but I always get like a lot of messages from like junior engineers asking, how do I get better, or how do I like understand, how do I get better at programming, or how do I get better at ROS2, or how do I get better generally at being a good robotic engineer? And most of them are young. So I do recommend a lot contributing to ROS2. Why do I say that? Because you learn quite a lot, and you learn from people that have a lot of experience. For in the case of NAV2, like Steve is a really good guy. He's a really awesome person. He helps you a lot. He actually helps me a lot of like, this implementation is bad. Why is it bad? Probably you can do it better like this. So you do learn a lot. why you actually contribute. So I do recommend you contribute to any project. For example, in the case of the previous talker, you can actually contribute to this project because you do learn a lot contributing to that project because you have people that have experience of that with that project. And but obviously, I would recommend to do it when you're younger because the more older you get, the less time you have to do this because in the end, you're not getting paid for this. It's something you do because you like to do it. So if you're young, I do recommend a lot contributing when you have time because trust me, when you get older, I'm not that old, I'm 27, but when you get older, it does get difficult. And when you start getting into relationships and stuff, you have less time. So I recommend you do that. NAV2, for example, is a great way to start. Or you can actually contribute directly to the ROS2 libraries, for example. And I think that's all. I hope you understand what I said, and I hope you at least learned a bit on external Kalman filters today. Thank you very much.
Yeah, thank you so much. This is actually a very wonderful session. I can see all the mathematics and all the Python and C++. So I hope some of us, we were not thrown off balance.
Yeah, that's why I tried to prevent a bit. That's why I didn't want to do a lot of mathematical equations because you can find them online and kind of trivial. So I think the problem is just defining the problem. That's way difficult. That's what I think way more difficult than just writing mathematical equations.
Yeah. So, guys, if you have a question, this is the time. Please ask your questions. I think I have, okay, some of the questions have been asked. So somebody's asking, what is RTK?
Okay. RTK is basically an enhanced GPS sensor. It gives you quite precise latitude, longitude, up to 10, I think sometimes up to 10 centimeters of precision. So the issue with GPS also is that it's not precise. Most GPS system have you guys noticed in your phone with Google Maps that sometimes it shakes a lot? That's basically because GPS is not that exact. Obviously, the version of GPS we have is not that exact. Obviously, the government have way more advanced GPS systems. But what RTK does, it gives you a really, really good positioning system of your of latitude, longitude, and altitude of no, not altitude, no, but yeah, it gives you really, really, really good. And for example, we were able to use in a previous company, we did operation landing with just RTK to tell you how exact it is. We use network RTK to do operation landing, so it's quite exact.
Okay, good. I hope you get that. So any other question? I think I probably have some couple of questions here, but anybody wants to ask question, you can go ahead. So somebody's asking if you have any books you can recommend or like a workflow, something. Hello? Hello, Steve.
Sorry. Can you repeat what you said?
Okay. Yeah, somebody's asking if you can recommend a book or something like a workflow or tools you can recommend.
For what exactly?
For Kalman filter, I believe.
Oof. First of all, in most cases, you don't have to implement your Kalman filter because there's heavy good implementation out there. Like for example, if in most let's say 80-90% of localization of mobile robotics, you can use the robot localization package. The downside to the robot localization package is I think it might get deprecated because in a few bit, but it works quite a lot. I would recommend to use it. Don't implement the Kalman filter from scratch because this package has a lot of years, and it works. And I think there's also a new one that's called Fuse. I think most likely the other downside to this Fuse is it does not support 3D, at least as of my knowing. So number one, I wouldn't recommend you to implement one. But in my case, I think I use like most my university notes. So actually, I can send you if you want. Just ping me. I'll send you some notes on Kalman filter if you really want to go deep in Kalman filters. But out of my head, I can't think of anything now. because I mostly use like different articles and papers, and depends on what I'm trying to do. So it's not exactly a specific book per se. I think that there are books on this, but I don't necessarily use a specific book per se.
All right, great. I think we'll probably get the notes from him, and then when we send email later, maybe this week or the next, then we will include that. So everybody will get that, including the video recording as well. Any other question? So by the way, I
Yep.
can see that.
Excuse me.
Okay. Okay.
Yeah,
Go
good
ahead, please.
afternoon. Yeah, it has been a wonderful section. And currently, I don't have a question, but I have an appeal. I'm happy to be in this community. I'm currently doing my master's in control and robotics at Central NAS in France. And by next year, February, I'll be looking at going for an internship. And I have been searching for internship all over Europe and Nigeria. So my appeal is, please, if there's any recommendation from the house or any offer, I will really be happy to know about. Thank you.
No
All right.
problem. I think one
Thank you for
advice
that.
I would give you is like contributing now that you're in university. Contributing also helps, like because you have like if you have a GitHub page, you have like a representation of what you have done. And also like if I can share my screen, so having like a GitHub page helps. GitHub, let me see if I can get it. For example, in my case, let me see. I don't know if I can see my screen. For example,
Yes.
like
Yeah.
I have a lot of repos, for example, because I did a lot of stuff in my career as a master's as a robotic engineer. I did a lot of it as a fine client. I did a lot of stuff. So having a public repo showing that you did a lot of contribution to show how you work, it helps a lot also to boost when getting jobs. So I would probably recommend you also try to literally contribute to other see that have like see I have a lot of codes online. So doing that does help you to at least put your foot on the door. And also, for example, if for example if you contribute a lot to one specific project, that person can recommend you, for example, for a job position. I've actually gotten a recommendation from Steve, for example, from certain positions or from people that I worked with in public projects. So I do recommend you do that. It does help. It does help a lot.
Thank you.
All right. That's good. It's a pleasure to have you, Sadiq. I guess maybe this is the first time here.
Yeah.
Yeah, so nice to meet you. Yeah, thank you. I think Samuel has a question. You can go ahead, please, Samuel.
Yes, good afternoon once again, Stevedan. Wow, what a session. Though I'll say I kind of lost track because a lot of the things was was a bit scattering. But my question is based on you said something about I've always had a problem understanding. See, this idea of the Jacobians has been one of my major problem. Yeah, explain this. So because you said about something about state transition, then you said where Jacobians come in, you said how the system explain what it means, like how the system evolved. I don't know if you can give a little explanation on that side. That's one. That's one. That's one. The next one, I think you also mentioned implementation of Kalman filter, extended Kalman filter, like the robot localization package, for example.
Yeah.
I think I want to understand something. There are parameters like process covariance. Yes. Yeah, and there's also, there's the sensor variance itself, like the covariance of the sensor itself. So what's the difference between those two? Because when tuning, that there's no place for like sensor variance. But there's a process covariance. So is it using the sensor variance underneath? So I just want to understand those things. Yeah, that's
okay. I also apologize for that because I didn't also know the level of the people that, because obviously to understand this, it requires a bit of base and in like all these mathematical equations and stuff. Let's start with the first question, Jacobians. Basically, when doing state estimation, you want to understand how your system changes, how the system changes with respect to time. normally in a linear system, it's no, let's say not even a linear system. It's basically derivative. It tells you, let's say in the case of a simple example is position. How do you know how your position have changed? To velocity. So what the Jacobian gives you, or what Kalman filter requires, is you have to give it something that tells it how your system changed. Same idea. Your velocity, how do your velocity change? Acceleration. But the issue with nonlinear system, so they basically, when you define your state equation and you have a cosinus or an angle somewhere there, most likely you have a nonlinear system, is it's not easy to get this. It's not easy to get that change. In the case of a linear system, and if you remember the ax plus by is a. It's just direct. So what Jacobian does is, but Jacobian basically does is it's partial derivatives of your state function with respect to your state. When I mean partial derivative, is like saying, let's assume, okay, I think I can show this example, which the 1D example should explain this well. Let me see, screen 1, screen 2. Okay, so in the case of the 1D, let me see. So in the case of the 1D, is the Jacobian is the partial derivative of this with respect to state. So it's like what you do in Jacobians is you derivate each of the values in your matrix with respect to each of the states. So you do, like, for example, the first this with respect to the first state, this with respect to the second state, this with respect to the first state, and this with respect to the second state. So for example, the derivation of this equation with respect to z is 1. The derivation of this with respect to velocity is dt. And if you guys understand, remember the derivation, the derivation of this with respect to z is 0, because you don't have any z in this equation, and the derivation of this with respect to velocity is 1. So that's basically Jacobians. It's basically the derivation of your state transition function with respect to the states, each of the states. She does it individually. The first one with respect to the first state, second state, third state, same thing. First state, second state, and you do the derivation all around the matrix. I know if that clears your doubt on Jacobians.
Yeah. Thank you very much for that explanation.
It's a technique that basically that's what makes it extended Kalman filter. They use Jacobians to estimate the change of your system. In the case of UKF, this is a different strategy, but basically the idea of UKF is this: it does use Jacobians to estimate the change of your system. And the second question you said about process noise and sensor noise. Yeah, so normally when you publish your sensor data, you include the covariance in the sensor message. So what robot localization does, it reads the covariance in the message.
Sorry.
What I mean by that, let's say emo sensor message ROS. You can see that there's something called covariance. And if you can see that each of the measurement has covariance. In the case of my implementation, I put this in a file, which basically put the standard deviation of each of my sensors, like the position. But most likely, your sensor, when it publishes data, it publishes also the covariance. The issue is Gazebo, that's why I actually included this here, because Gazebo, for some reason, which is I don't know why, does not publish this covariance. That's why I had to put it manually, because when I defined the model SDF, I put each of these covariance. For example, I don't know if I can find one that like, yeah, see, for example, in this case of the GPS, I include this covariance in the system. But for some reason, Gazebo does not publish this data. I don't know why, but it doesn't. So this is just a way to, it's like a partial solution just for this specific presentation. But most likely, your sensor, or when you create a sensor package, you should publish in that sensor the covariance itself. And each of the sensors position, EMU, includes the covariance parameter. And the other one, which is the process, that's why you, in the robot localization, you have just the process, because that's actually what you have to tune, because the other one already comes from the sensor. I don't know if that makes sense.
Yeah, I think it makes sense. So this one we have to tune it manually. The other one comes from the sensor.
It should come from the sensors. Like in most cases, these values are not correct. So what people do is they include the bias in the state estimation. Like they put the bias of the acceleration data, and so you can actually increase the state you want to estimate, and include the bias of each of the sensors. To consider that there's a probability that the covariance is wrong. So I just try to estimate in real time the covariance of each of my sensors. Also, this is also possible to include the accuracy of your system. Also, that's also one approach that people normally do when doing Kalman filters.
Yeah, thank you very much, Stevedan. This is really amazing.
No problem.
Yeah,
All right. So
we should speak.
yeah, I think there's another question, but I want to say that we've actually gotten to the end. But if you want to stay back, that's fine. Just know that we are actually done. So if you feel like you want to stay back, then that's fine. I don't know if our speaker can take maybe one or two or three more questions, actually.
Sure, no problem, no problem. I have time, no
Uh,
problem.
All right. So Emmanuel is raising hand. So Emmanuel, you can go ahead, please.
Yeah, all right. Am I audible?
Yeah.
All right. Thank you very much. Thank you very much, Steve. Very wonderful session. I could relate to a whole lot of the things you shared, the concepts you shared, right? So I don't really have a question pertaining to the particular topic, but I just want to ask a general question. This is my first time in this community, and basically what I'm asking is if we can get like a sort of career mentorship in robotics field, because I realized that, and this is not just about me, right? I realized that there are a lot of people who are interested in this field. You find them studying related courses in school, mechanical, electrical, and the likes. And when they are done with studies, they don't really know, they don't have the guidance, or they don't even know how to get started, in robotics. And so you see them branching out into adjacent field like web development, right? Because of the ease of access, and they just don't know how to get started in robotics, right? And for me, I believe that fields like robotics and digital hardware are like, if not one of the most, if not the most, one of the most important course.
Hello, Emmanuel. Sorry
Yeah.
to cut you short, but because of our limited time, you have to go straight to your question, please.
Yeah, so my question is, can we have, I don't know, maybe we'll have one of those sessions or their materials, sort of career mentorship.
Okay, so let me be honest, because I've also been in that position also, because I've also, like, at some point in my career, especially when I finished my university, because I think when I did my bachelor's, I had the advantages of going with a supervisor that instilled the need to help open source community, so to giving back to the community. It sounds strange, but it's something that I think I got told a lot by my supervisor, and I do believe in it. But from a realistic situation, everyone is busy. Let's just start from there. Everyone is busy, and because I'm just telling you how I went through it when I started